Friends, today let us discuss on remote sensing, the basic concept of remote sensing. So what is remote sensing? It is nothing but sensing of an object without any physical contact with the object. That means we are making use of various sensors for remotely collecting the data. So in fact, see, our eyes are acting as sensors mounted on human body, and when you are reading these words or definition of remote sensing, you are employing remote sensing because without any physical contact you could be able to gather the required information. So it is the science and art of obtaining information, useful information about the objects, and then we are analyzing that acquired data. So then we are generating different kinds of maps, but in this process there is no physical contact with the object. That means we have the solar energy which reaches the surface, it interacts with the surface features, and retransmission will take place. This retransmitted energy will be recorded by the sensors present in the aircraft or spacecraft. So this is done by sensing and recording reflected or emitted energy, and then we are processing and analyzing, and at the end we are extracting some useful information about the Earth's surface features. Next slide. See, in this process, the basic concept involved in remote sensing is the data acquisition. So we have the sun here. Sun is the chief source for the electromagnetic radiation. Then before it reaches the surface, it has to pass through the atmosphere. Then scattering and absorption will take place. Combinedly, this mechanism is called as atmospheric attenuation. But what happens when the energy passes through the atmosphere? See, there is a mechanism called scattering. It is nothing but dispersion or diffusion of radiation by the atmospheric particles. And depending upon the interacting electromagnetic radiation and the atmospheric particle size, we have Rayleigh scattering, we have Mie scattering, and we have non-selective scattering. In the case of Rayleigh scattering, see, the interacting electromagnetic radiation will have larger dimension than the atmospheric particles. So because of that, we are seeing the sky as blue, because the shortest wavelength of the visible light, blue is the shortest wavelength, which scatters more dominantly than the other wavelength. Then in the case of Mie scattering, the interacting electromagnetic radiation and atmospheric particles, they have equal dimension. In the case of non-selective scattering, which is the reversal of Rayleigh scattering, means the atmospheric particles will have larger dimension than the interacting electromagnetic radiation. Normally, due to this scattering effect, the contrast of the image gets reduces. See what happens, in addition to this reflected energy, the backscattered energy from the atmosphere is also being recorded by a sensor. That means there will be a noise from the atmosphere. So that is why before going for any kind of image analysis, we must remove this noise which is incorporated because of the scattering effect. That will come under digital image processing. But finally, part of the light will succeed in reaching the surface. Again, atmosphere is made up of gaseous molecules and dust particles. Atmosphere does not allow all the electromagnetic radiation to pass through it. And all of you are familiar about the electromagnetic spectrum, which ranges from gamma rays up to radio waves. We have gamma rays, X-rays, UV rays, then we have the visible region of the spectrum, then we have near infrared, mid infrared, thermal, as well as the radio waves. So all these wavelengths are not at all passing through the atmosphere. Gamma rays, X-rays and UV rays are blocked by the atmosphere. But the remaining wavelengths like visible, infrared and thermal as well as microwave range of the spectrum will reach the Earth's surface, because atmosphere is acting as a transparent media for those wavelengths. That is called as atmospheric windows. That means where the absorption is minimum or where the atmosphere is acting as a transparent media. That is called as atmospheric windows. So finally, part of the light will be reaching the Earth's surface. It interacts with the Earth's surface features and retransmission will take place. This retransmitted energy will be recorded by sensors present in the spacecraft as well as in the aircraft. But in case of India, so we have different kinds of satellites orbiting over the globe. So we have a Earth receiving station located at Hyderabad called National Remote Sensing Service Center. So whenever the Indian satellites passes over the Indian subcontinent, using these antennas, they receive the satellite signals, they process the satellite data and supply it to the users. So up to this stage it is called as data acquisition. So in remote sensing normally we have two things that is data acquisition. We have to acquire the data using satellites or aircrafts. Without any physical contact, we are remotely collecting the data. The upwelling electromagnetic radiation is being recorded by the sensors present in the aircraft or spacecraft, and that when we are analyzing, we will be able to extract some meaningful information from the photographs or from the images. Next slide. So there are two types of remote sensing. One is active, the other one is passive. If you are using camera with flash, so that is called as active remote sensing. And if you are taking the photograph without flash, so during night time when you do not have sufficient light, you are making use of the flash. That means it is active remote sensing. And if you are taking the photograph during daytime by using naturally occurring electromagnetic radiation, that is called as passive remote sensing. So next slide. So here sun is the chief source. See, during daytime you are taking the photograph, so energy will be reaching, it interacts with the earth surface, which is then retransmitted energy will be collected through the sensors present in the satellites. So most of the satellites make use of this technique, passive. They are making use of this naturally occurring electromagnetic radiation as a source. Then we have active remote sensing also, especially in the microwave region. See, radar stands for radio detection and ranging. The microwave energy is being generated and that energy has been sent towards the object. That means it is an active source. Then the return signal will be again recorded by the same sensor. So that is nothing but active remote sensing. Next slide. So this we have already discussed. I said the basic concepts of remote sensing involves data acquisition and data analysis. So you have the sources of energy, then it has to propagate through the atmosphere, then energy must interact with the earth surface features, then retransmission should take place. This retransmitted energy will be recorded by low altitude aircrafts, medium altitude aircrafts from 10 to 15, maybe 30 to 40 kilometers, and from 700 to 900 kilometer orbiting satellites at an altitude of 700 to 800 kilometers. We have the polar or sun synchronous satellites are there. So they record the signals. So up to this stage it is called as data acquisition. Then once we have the data which are available in the hard copy as well as in the soft copy mode. Soft copy is nothing but the digital mode. Then this part is called as data analysis. We are carrying out the analysis through visual technique or through digital techniques. In the case of visual techniques, we are making use of various recognition elements criteria. In case of aerial photographs, we are making use of some pocket stereoscopes, mirror stereoscopes, then parallax bar and all to make the measurements. Then in the case of digital image processing, we are making use of the computers. So digital image processing involves the manipulation and interpretation of digital data, and we are carrying out the analysis using a powerful software packages and computers, and at the end we are deriving some useful information. This is what the information extraction. Finally the maps will be generated or the information will be available in the bar diagram form and all. So useful outputs will be generated. This is about the data acquisition and data analysis stages. Next slide. So here I said light is a form of energy which itself is not visible but makes other bodies visible. So electromagnetic energy which is having both electrical and magnetic properties. When light is incident on a body, it reflects a portion of light. So according to its ability to reflect. So part of the light will be reflected, part is absorbed and part is transmitted through the object. So that will be different for different earth surface features. Next slide. See, this is the electromagnetic spectrum. We have gamma rays, X-rays, UV rays. Then comes the visible region. See, it is from 400 to 700 nanometer or 0.4 to 0.7 micrometer. See, our eyes are acting as sensors mounted on human body, which is capable of sensing the surface features only in this region of the electromagnetic spectrum. Beyond that, we cannot sense. But like our eyes, there are eyes present in the satellites called sensors, which are capable of sensing the surface features beyond the visible also. They can sense in the infrared. That is what we say near infrared, mid infrared, thermal infrared, as well as in the microwave region of the spectrum, longer wavelengths, millimeter to meter, because microwave has the penetration capability. So for some of the applications, like if you want to know the thickness of the glaciers present in the North Pole and South Pole, your optical sensors, which means optical means visible and infrared, They cannot penetrate through the clouds, and even during night time we cannot collect the required information. But in the case of microwave remote sensing, it has the penetration capability. Irrespective of the weather, we could be able to gather the required information through microwave remote sensing. Next slide. So these are the electromagnetic spectrum ranging from gamma rays to microwave, see, millimeter to meter wavelength. We are making use of the longest wavelengths. But shorter wavelength means they have the highest energy content. Longer wavelength means lesser the energy content. So it is difficult to devise or develop the sensors in the microwave region of the spectrum. That is why normally we go for active microwave remote sensing technique. This is nothing but the electromagnetic spectrum normally used in remote sensing. Next slide. See, energy interactions. I said in the beginning, see, when it interacts with the atmosphere, again absorption and all takes place, absorption, transmittance, scattering and all takes place. Finally, part of the energy will be reaching the Earth's surface, and the return signals will be gathered by the satellites. So, absorbed, scattered, reflected. So, like that, energy will be having different characteristics. Next slide. So, atmospheric windows. See, if you see here the atmospheric windows, see, the visible region can pass through the atmosphere, then part of the thermal region, then microwave region. The remaining wavelengths cannot pass through the atmosphere. So, because atmosphere is made up of gaseous molecules, dust particles, you have the water vapor, then carbon dioxide, ozone and all, they absorb the electromagnetic radiation. Only part of the light will be reaching the surface. That is what we have the atmospheric windows in the visible region, we have in the infrared region as well as in the thermal and microwave region of the electromagnetic spectrum. Next slide. See, this is very important because whenever the energy interacts with the Earth's surface features, part of the light will be reflected and part is absorbed and part is transmitted. See, whether these three will be similar for all the surface features? No, it differs because if it is a beach sand, it may reflect maximum light. If it is a water body, which absorbs most of the electromagnetic radiation. So that means reflection, absorption and transmittance will be different for different surface features, and that can be expressed by a mathematical equation called Ei lambda. Lambda is nothing but which represents the wavelength. This is the incident energy. Ei lambda means Er lambda plus Ea lambda plus Et lambda. That means reflection, absorption and transmittance will be different for different Earth surface features, and that is the basic principle when we are interpreting the satellite images or aerial photographs. We must know which surface features will behave or which will show highest reflectance. So which will absorb all the electromagnetic radiation. Blackboard, which may absorb all the electromagnetic radiation. Your computer screen absorbs most of the electromagnetic radiation. It looks black. In a similar way, maybe white objects reflect maximum light. That means reflection, absorption and transmittance will be different for different Earth surface features. And one more thing we must remember here. This absorbed energy will be transmitted back during night time. That is called thermally emitted radiation, and normally the satellites record not only the visible region, this reflected energy, that are also recording the emitted radiation in the thermal region. Then we have the transmitted energy and all. So these again will be different for different Earth surface features at a different wavelength. See, normally in case of photography, when I click the camera, I am getting one output. But it is not in the case of satellites. Whenever a particular satellite passes over an area, it records the signals at a different wavelength of the electromagnetic spectrum. Simultaneously, you are getting the data in the blue region of the spectrum. I said in the beginning, in the visible region of the spectrum, we have blue spectrum 400 to 500, green is from 500 to 600, red is from 600 to 700. From 700 onwards, it is the near infrared. So simultaneously we are gathering the data in 4 different spectral bands. Let us say in the case of multispectral data, if we collect the data in 4 bands, why we need those 4 bands means, again the reflection, absorption and transmittance will be different for different surface features. That is point number 1 when we are considering this equation. The second importance is, the second point is again these 3 will be different at different wavelength of the electromagnetic spectrum. That is the advantage in case of satellite remote sensing. If you are not in a position to differentiate two surface features at one particular wavelength, we can think of going for the second band, the third band, the fourth band. Like that we are getting the multispectral information. Next slide. See how much of energy reflects back from the Earth's surface features. It depends upon the material type and condition of the Earth's surface features. How much of energy is reflected, how much of energy is absorbed, and how much of energy is transmitted. These three will be depending upon the material type and condition of the Earth's surface features, and that is the basic principle. Based on these variations, we will be able to differentiate the Earth's surface features on a particular image. And these spectral variations are expressed as colors. See, suppose why we are seeing this as green, vegetation looks green, because vegetation reflects in the green region of the electromagnetic spectrum, which absorbs blue and red portion of the electromagnetic spectrum, and yellow means it is reflecting it in the yellow portion, green is reflected in the green region of the spectrum, like that red is reflected. But see, when the plant is subjected to some sort of stress, the chlorophyll production gets reduces. The result is it starts to reflect some part of the red region of the spectrum. So combination of green plus red results yellow patches. Yellow, if you see yellow vegetation, yellow color for a particular type of vegetation, definitely we can say that is a diseased vegetation. See, like that, based on the color, we will be able to differentiate the surface features. Next slide. See, if two surface features are indistinguishable in one spectral range, it will behave differently in another spectral range. That is what I said in the beginning. When we have multispectral data, and if you make use of this multispectral data to differentiate the surface features, in one wavelength both the surface features may show similar reflectance, but you have different spectral bands. Make use of those spectral bands and try to differentiate the Earth surface features at different wavelength of the spectrum. Even within a given feature type, the proportion of reflected, absorbed and transmitted energy vary at different wavelength. Then spectral variations in the magnitude of reflected energy is utilized to discriminate objects. Next slide. See, now when we talk about spectral reflectance, how much of energy reflected back from the Earth's surface feature, and if you divide it by the amount of energy incident upon the object, let us say a particular surface feature reflects 60% of the light, 60 divided by 100, and if you multiply it by 100, you are getting the spectral reflectance in percentages. So spectral reflectance is always measured in percentages, and if you plot the spectral reflectance versus wavelength, you are getting the spectral reflectance curve. Next slide. See, this is nothing but the amount of energy reflected by the object, and you divide it by the amount of energy incident upon the object, and if you multiply it by 100, you are getting the spectral reflectance in percentages. Next slide. And this is of course a spectrophotometer. This you can make use of in the field. So you measure the spectral signatures of different surface features, and if you correlate that data with the satellite derived data, if they are matching, your interpretation will be more accurate. This is to get the spectrophotometer. See, you can measure the spectral signatures of different surface features based on this handheld spectrophotometer. And this is of course a ground platform. I said in the beginning, normally in remote sensing we go for ground platform, aerial platform and space platforms for collecting the data. Without any physical contact, we are remotely collecting the data using the ground platform, aerial platform plus space platform. Next slide. See, if we draw the spectral reflectance versus wavelength, see, we are getting the spectral reflectance curves. Why? What is the necessity of plotting the spectral reflectance curve? Next slide. See, on one axis we are representing the reflectance values. In another axis we are representing the wavelength starting from 0.4 to 2.5 mid-infrared region. And this is spectral reflectance. Spectral reflectance is always expressed in percentages. If you divide the amount of energy reflected from the surface, divide it by the amount of energy incident upon the object and multiply it by 100, you are getting the spectral reflectance in percentages that you have to plot against the wavelength. See, this is the healthy vegetation curve, the green line. But here if you see, at green portion of the spectrum, vegetation reflects more energy. That means for us, vegetation looks green and blue and red get absorbed. But I said in the beginning, the sensors present in the satellites are capable of sensing not only the visible, we are capable of sensing only the visible region, but the sensors present in the satellites, they can sense beyond the visible region of the spectrum. And if you see here, the vegetation reflects maximum light in the near infrared region of the spectrum. About 50% of the light gets reflects in the near infrared region of the spectrum. That is why normally for vegetation mapping we go for near infrared bands because of the highest reflectance of the visible which reflects in the green, but the satellites are recording the data using visible plus infrared. So you have two depressions here at 1.4 and 1.9. That is mainly because of the water molecules present in the leaves. This is the standard curve for vegetation, and in a similar way you can see there are two depressions even for soil because of the moisture content in the soil. There are two depressions, but it is also showing the increasing trend. In the case of water bodies, see from 0.4 up to 0.75 there is a reflectance. After that there is no reflectance. That means water bodies absorb all the electromagnetic radiation and will look black in the near infrared region as well as in the mid infrared region. So to get the water body information, we must go for again the near infrared band. See, by plotting the spectral reflectance curve, we will get some idea about the spectral characteristics of the Earth surface features, and based on that we can select which are the best bands for a particular application. Here I will go for near infrared band for vegetation mapping because I know the fact that vegetation reflects maximum light in the near infrared region of the spectrum. In a similar way, water bodies absorb the electromagnetic radiation from 0.7 onwards. So even for water body delineation, near infrared bands are most useful. Next slide. So what is the reason? What are the reasons why vegetation shows the peak and depression? See, especially in the green region, see that is because of the chlorophyll absorbs blue and red region of the spectrum, it reflects in the green region. So it is mainly because of the leaf pigment. Then because of the cell structure, there will be a highest reflectance in the near infrared region of the spectrum. Then again I said 1.4 and 1.9 as well as around 2.7 you have the absorption because of the water content in the leaves. So this is a typical spectral reflectance curve of a vegetation. Next slide. See, now our aim is when the satellite images are provided to us, our aim is to demarcate different types of surface features. Now let us see. I said we have the multispectral data available with us, and when you go for this multispectral data analysis for differentiating different kinds of vegetation, see here we have two types of vegetation. One is deciduous trees. Deciduous trees means they are shedding their leaves at a particular season. Then we have narrow-leaved species called coniferous trees. Let us say we have to differentiate these two types of vegetation of the Western Ghats of a particular column. What I will do, I will go for the blue region of the spectrum to differentiate these two types of vegetation. I will not succeed because both of them are having almost similar reflectance. Again in the green region, the blue I will not succeed. In the green also both of them are having similar reflectance. In the red both of them absorb the radiation. But you see here in the near infrared, that is from 0.7 onwards, see this will have lower reflectance. Coniferous trees are having lower reflectance, whereas deciduous trees are having more than 40% of the reflectance. Based on this, now I can easily demarcate the boundary between the two, where I have the deciduous trees, where I have the coniferous trees. That is how I can go for multispectral data to differentiate different types of surface features, because it is clear from the spectral reflectance curve that different surface features will behave differently at different wavelengths of the electromagnetic spectrum. That is nothing but when energy interacts with the surface features, different surface features will behave differently. Next slide. See, this is nothing but normalized differential vegetation index. See, whenever you go for this kind of healthy versus stressed plant, suppose I have to show where the healthy vegetation is there, where the diseased vegetation is there. See, if you have the healthy vegetation, suppose in an area, if you see a healthy paddy in a larger area, see, with the help of this vegetation status, even you can calculate the yield. From the sowing season till the harvesting season, you can monitor the status of vegetation by making use of this vegetation indices. In the sense, see, if you take the ratio of near infrared and visible red, NIR minus visible red, this is nothing but spectral reflectance, you divide it by NIR plus visible red. See, here the vegetation reflects maximum light in the near infrared, and in the red it will be less reflectance, more absorption. And if you make use of that formula, you are getting a value of 0.72. That means higher the NDVI value, the healthier the vegetation. In this case, when the plant is subjected to some sort of stress, the chlorophyll production gets reduces. The result is it turns to yellowish. That means here the NDVI value is less, means it is a diseased vegetation. Now with this, I can say where you have the healthy vegetation, where you have the diseased vegetation. And from the sowing season till the harvesting season, if you monitor the status of vegetation, and based on that even you can calculate the yield, how much of yield will be there in a particular area. Next slide. So in a similar way, water, highly silted water and aggravated soil erosion results higher visible reflectance than clear water. Normally, suspended sediments concentration is more, means turbid water will have higher reflectance than clear water. And even if the water bodies are having the higher concentration of algae or weeds, that will increase in chlorophyll, that means higher reflectance in green spectrum and lesser reflectance in blue spectrum than normal water bodies. So based on this, we will be able to differentiate where we have the clear water, where we have the suspended sediment rich waters are there. So if the water is very clear, sometimes you can make use of this electromagnetic spectrum even to determine the bathymetry, because it can penetrate up to few meters provided the water is very clear. Next slide. Soil summary. In the case of soil, see, increases in moisture content means there will be decrease in reflectance, because moisture means it absorbs the radiation. In a similar way, increase in particle size means there will be a decrease in reflectance. Then if the organic matter increases, again there will be a decrease in reflectance, and increase in iron oxide means there will be a decrease in reflectance. This is about the soil. So we have different types of soils are there. So how to differentiate the soil and what are its characteristics, that we can study with the help of remotely sensed data. Next slide. Okay, up to here we have discussed about the basic concepts of remote sensing. So in remote sensing, normally we make use of this electromagnetic radiation as a source. And see, in the case of digital data, again these are expressed by digital numbers, and in most of the cases the satellite data will be recorded from 0 to 255. Whatever the analog values are there, that will be converted into digital numbers. I said in the beginning, we have a center located at Hyderabad called National Remote Sensing Service Center. See, whenever these satellites record the signals, the analog values, it will be if it is a reflected energy, that will be in the analog form, that will be converted into digital numbers, and you can see here the digital numbers. And the lower digital numbers means it absorbs the radiation. Higher the digital numbers are closer to 255, it means they are the brightest objects. So water bodies will show lower reflectance. If it is a shaded area or shadow area, you will have lesser reflectance. If it is a desert or sandy area, you will have higher reflectance. So what happens when the energy reaches the Earth's surface? It will be interacting with the Earth's surface features, and retransmission will take place. This retransmitted energy will be recorded by sensors present in the satellite, and this mechanism is called as remote sensing. And remote sensing has wider applications. You can make use of this technology for number of applications. At the end, you can generate some useful resource maps by using this remotely sensed data. I think it is clear for all of you.